Hello friends, welcome to Mechanical Engineering online classes. Today's lecture will be delivered by Miss Shravani Sriramoju.
Now let us see the processing of n jobs processed on 3 machines. The first assumption is that only 3 machines are involved. Let the 3 machines be A, B and C for example, and the order for each job is same. So let that be A, B and C. Means every job will first go to machine A, then that job will then go to B and then C. So A, after A it is B, after B it is C. So this is the order. And before we find the least total elapsed time, we assume that we know the actual or expected processing times for every job and on each machine. That is the third assumption. Now using the processing procedure which has been suggested by Bellman and Johnson, we know how to find the optimum sequence for n jobs that are processed on 2 machines. But now because this is 3 machines, Johnson had given 2 conditions. So if if at least one of the 2 conditions is satisfied, then we can apply the procedure laid down by them. Let us see what the 2 conditions are. So if the processing order is that every job is first going on to machine A, then that job will go to machine B. After processing is completed on machine B, then it will go to machine C. The processing order for every job is the same. So in case this is the order, first A, then B and then C, then the conditions are the minimum processing time on machine A should be greater than or equal to the maximum time or maximum processing time on machine B. Whereas A is the first machine the job should go to, and B is the second machine the job should go to. The second condition is that minimum time on machine C. Minimum time on machine C. C is the machine where every job is going last. So the minimum processing time on machine C should be greater than or equal to maximum time on machine B. So A and the processing times on A and C, the minimum times on A and C, either of which should be greater than or equal to the maximum processing time on machine B. So even if one of these 2 conditions is satisfied, then we can apply the Johnson rule as follows. So both the conditions may be satisfied, or if at least one condition is satisfied, then we will assume 2 fixtures machines. Let the fixtures machines be some machine G and machine H, such that the processing times on machine G, say GI, is nothing but AI plus BI. So A plus B is G, and the H machine can be written as, the processing times for H machine is written as BI plus CI. So now we will have the same table like that in previous video, processing n jobs on 2 machines. So here the 2 fixtures machines are G and H. The table is taken down as A plus B for G and B plus C for H, where A is the first machine, B is the second machine, C is the last machine, which every job will visit. What if none of the conditions is satisfied? If none of the conditions is satisfied, then all the possibilities must be found to find the optimum sequence answer, and for that we have several other methods, like heuristic methods are available. Let's not go into that. Assuming that we have at least one of the 2 conditions being satisfied, then we can frame 2 fixtures machines such that the first machine is a combination of first and second machine, the second machine is a combination of second and last machine, this way. So let us understand this using an example. Let us say a question to find the optimal elapsed time and idle times for the following problem, where jobs should go in order: first turning, then threading and then knurling. All the times are given in terms of minutes. The number of jobs given is 6. So job 1 will take 3 minutes on turning, then it will take 8 minutes on threading and then 13 minutes on knurling. Similarly, job 2 will take 12 minutes on turning, then 6 minutes on threading and 14 minutes on knurling, and so on. Job 6 will take 11 minutes on turning, 1 minute on threading and 13 minutes on knurling. Now this is an example of processing n jobs on 3 machines. So let us see if any of these conditions are satisfied. the order is turning, threading and knurling. So let this be machine A, this is machine B, this is machine C. Then minimum time on machine A should be greater than or equal to maximum time on machine B. What is the minimum time on machine A? Minimum time on machine A is 2. The first condition. Minimum time is 2. Let us see if it is greater than or equal to the maximum time on machine B. What is machine B? Threading. Maximum is 8. So this is not satisfied. Then let us check with condition number 2. The minimum time on machine C. What is the minimum time on machine C? On knurling. The minimum time is 8. This one. Is if 8 is greater than or equal to maximum time on machine B, which is threading. Maximum time on machine B is 8. So this is 8 is greater than or equal to 8. This condition is satisfied. So because at least one condition is satisfied, we can now write this 3 machine problem. We'll convert the 3 machine problem into a 2 machine problem using 2 fixtures machines. Let GI be equal to AI plus BI and HI is equal to BI plus CI. So let us write the new table for all the jobs. Jobs are from 1 to 6, and now we will be writing this as a 2 machine problem, where the first machine is sum of the first 2 machines, means we will write it for the processing times. So A plus B is what? For first job it is 3 plus 8, which is 11, and H is nothing but B plus C. So for first job it is 8 plus 13. 8 plus 13 is 21. Similarly for the second job, for G it is 12 plus 6, which is nothing but 18, and for H it is 6 plus 14, which is 20. Similarly we will write for the third job, fourth job, fifth job and sixth job. For 3 it is 5 plus 4, which is 9, and for H it is 4 plus 9, which is 13. For 4 it is 2 plus 6, which is 8, and for under H it is 6 plus 12, which is 18. Job 5G is 9 plus 3, which is 12, and for H it is 3 plus 8, which is 11. For 6th job it is 11 plus 1, that is 12 under G, and under H it is 1 plus 13, which is 14. Now we will apply the same principle of finding the sequence as we have applied for in the previous video, processing of n jobs through 2 machines. But here one thing I would like to tell you, because it is given in the question that every job will go in the order of turning, then threading and then knurling, and the given table is also in the same sequence. It is turning first, threading next, knurling in the last. But in case the order is mentioned like, if it is mentioned as ABC, then and the table is also ABC, we have taken down in that fashion only. But if the order is given as, say, some B first, C next and A on the last, if the order is B, C, A, then I recommend you rewrite the given table in the given order. B, you first write the B column, that is the threading column, then you write the C column, which is the knurling, then you write the A column, which is turning. So you rewrite this, and in that case, if at all at least one of the conditions is satisfied, then our G will be this B plus C will be G, and this C plus A will be H. Alright, so it is important that you check out what order is given. Depending on that, if at least one of the 2 conditions are satisfied, then the job that is going first to first machine and then the second machine, the sum of the first machine and the second machine is G. It might be BC or it might be CA, it might be AB or whatever is given, that should be taken. So whatever the order is given, and if that order is not matching with the given table, I recommend you rewrite the table and then work out the problem. Then depending on the given sequence, we will rewrite the table in the form of the given sequence. Then we will write the GH, and then all the other methodology is same. So using the rules that we have already learned in the previous video of processing n jobs through 2 machines, I am writing the optimum sequence. How do we write the optimum sequence? How many jobs are there? Those many slots I am just making. Suppose this is for the sequence for that are the order in which they are going for machine G, say. So we will find the minimum among the two columns. What is the minimum among the two columns? It is 8. And this 8 is for G machine, the first machine. So our fourth job will first go to first machine. So this is 4. Once this is already done, now the next minimum is 9 minutes for job 3, that will go to, that is under G. So after 4, next job is 3, that is going to machine G. So this is also done. Now what is the other one? What is the next minimum in the remaining? It is 11 for job 1 under machine G and 11 for job 5 under machine H. So because job 1 is having minimum for machine G, job 1 will first go to machine G, and job 5 is having minimum for under machine H, which is the second machine. So because this 5 is minimum for second machine, it will go last to the first machine. So this 5 will be written from the right side. So this is done. Now what is remaining? 18, 20, 12 and 14 are remaining. 12 is the minimum for job 6 under G. So 6 will go here. Now all that is pending is 2. So this is the optimum sequence. Now once the optimum sequence is there, we can write the time schedule. So we have actually used G and H only to find this optimum sequence, but actually every job should go to 3 machines, right? So all the 3 machines are having these different processing times, right? So we have to write the schedule for all the jobs, for all the 3 machining processes, for all the 3 operations. The significance of G and H is only until we find the optimum sequence. Now the optimum sequence is known to us. Let us write the jobs. So this is the order in which jobs are going to different machines. What are the different machines? First they will go to turning machine. So we will write the time in and time out for each job. Then they will go to the threading machine. Here also we will write the time in and time out. Finally they will go for knurling operation and knurling machine. Then we will write down the time in and time out from the given table. Now fourth job is the first one that is going for the first machine. So job 4 will take 2 minutes on turning machine. So if we start counting our time from 0, it will go at 0 minute to turning machine, and after 2 minutes it is done. Now fourth job is out from the turning machine, and since we are not considering the time between job shifting from machine to machine, we are assuming that from second minute it is available on threading machine. How many minutes will it take on threading machine? It is 6 minutes. So from 2 minutes it will add on from 2 to 8. 6 minutes from 2 minutes is 8 minutes. So at the from 8 minutes it is free. The threading machine is free after 8th minute. And once job 4 is out at 8th minute, it will go immediately on to the knurling machine. How many minutes does that need? It needs 12 minutes on knurling machine. So from 8 it will work 12 minutes. So total is 20 minutes. So job number 4 completes all its operations. All the operations on job 4 will be done by the end of 20 minutes starting from 0. Now after fourth job, which first went to turning machine was busy in the first 2 minutes. So in the second minute, turning machine is free. So job 3 will go on to turning machine at minute 2. And the time it requires on turning machine is 5. So from 2 it will take 5 minutes. So this will be 7. Now job 3 is ready. It already completed going to turning machine. So it should go to threading machine. But can it go to threading machine at the 7th minute? No. Because threading machine is already busy up to 8 minutes. So that 1 minute job 3 will wait, and at 8th minute the threading machine is free, right? So in the 8th minute job 3 will go to threading machine. And on threading machine how many minutes it requires? 4 minutes. So it will be 12 here. Now by 12 minutes job 3 already completed its turning operation and threading operation. Now it should go to the knurling operation, but knurling machine at minute 12 to 20 it is busy with job 4. 8 to 20, right? From 8th minute to 20 minute it is busy with job 4. So only after this 20 minutes is done for job 4, job 3 can be taken onto the knurling machine. So at 20 minute our job 4 is completed and knurling machine will be free only after this 20 minutes. On that 20th minute job 3 will be taken up. How much time does job 3 need on knurling machine? It is 9. So from 20 it will need 29. In a similar fashion we can write for all other jobs. Now after 7th minute turning machine is free. It has completed job 4 in 2 minutes and by 7th minute it has completed job 3. Now job 1 is ready to go on to turning machine here. So in time of job 1 is 7. How much time does it need on turning machine? 3 minutes. So it will be 10 here. And in 10th minute turning machine is free from job 1. So 6th job will come at 10th minute. 6th job needs how many minutes on turning machine? 11 minutes. So 10 plus 11 is 21. Now at 21 minute turning machine is free. So now job 2 will enter turning machine at 21st minute. So how much time does it need? 12 minutes. So 21 plus 12 is 33 minutes. Now 33 minutes, after 33 minutes turning machine is again free and so job 5 will go at 33 minutes. How much time does that need? It is 9 minutes. So 33 plus 9 is 42. So from 0th minute to 42 minutes turning machine has completed all the operations on all the 6 jobs. Now job 1 after its operation on turning machine it is 10 minutes by then, but that it have to then go to threading machine. But can it go to threading machine at time 10? No, because during that 10 minutes job 3 is busy on threading machine. So threading machine will be free only after 12 minutes. So after this 12 minutes, after threading machine is ready, then from 12th minute job 1 will go on to threading. Job 1 needs how much time on threading? 8 minutes. So 8 minutes from 12 is 20. Similarly, now 20th minute up to 20 minutes threading machine is busy. From 2 minutes to 20 minutes threading machine is busy. From the 20th minute itself it can take the next job, which is job 6. But is job 6 free? No. Job 6 is in the 20th minute it is busy on turning machine. So after job 6 is free, after 21 minutes it will go on to threading machine. Now how much time does this need on threading machine? 1 minute. So in 1 minute it will be done. This is 22. Now our threading machine is free after this. It can immediately take up the next job. But is the next job ready? Is the next job available? No. The next job is during the 22nd minute. It is on turning machine. It takes a lot of time on that. Job 2 requires 12 minutes there. So if you see from 21, only job 2 can come out of turning machine from 33 minutes. After 33 minutes. So its in time is 33. So now at the 33rd minute job 2 is ready to come on to the threading machine. How much time does it need on threading machine? 6 minutes. So 33 plus 6 is 39. Now threading machine is again free at the 39th minute. But job 5 is not ready to come. Job 5 will finish its operation on turning machine only after 42 minutes. So at 42nd minute it will come on to threading machine. How much time does it need there? 3 minutes. So this will be 45. Now let us fill these gaps. Job 1 by 10 minutes it has completed its work on turning machine. By 20 minutes its threading operation is also completed. From 20th minute it can work on knurling, but knurling machine is busy with job 3 up to 29 minutes. So job 1 will go on to knurling machine only after job 3 is completed. Job 3 completes at 29th minute. So from 29 only job 1 can go on to knurling machine. How much time does it need? This 13. So 29 plus 13 is 42. Now knurling machine is busy up to 42 minutes. So sixth job, though it has completed its work on the previous machine 22 minutes only, but it has to wait until knurling machine is idle. A knurling machine is empty. Knurling machine is working on job 1, job 3 and job 1. So by 22, in this 22, while this 22 is happening, during this 22nd minute, job 3 is on knurling machine. So after job 3 is completed, job 3 will be completed at 29 minutes, and after that job 1 will go, and it will take up to 42 minutes. So only after this 42 minutes can job 6 can be taken on to the knurling machine. Okay, so in time for job 6 is 42. How much time does it need on knurling machine? 13. So 42 plus 13 is 55 minutes. Now similarly, job 2 should go to knurling machine. It is ready in the 39th minute itself, but the knurling machine is not ready. It will be ready only in the 55th minute. So job 2 will go to knurling machine in the 55th minute. How much time does that require? 14. So 55 plus 14 is 69. Now job 5 is ready to go on to knurling machine from 45th minute itself, but because in the 45th minute knurling machine is busy with job 6, 45 comes here for job 6, and after job 6 is completed, only then job 2 will go, and by then it will be 69 minutes, and only in the 69th minute our job 5 can go. Job 5 will require how much time? 8 minutes. So 69 plus 8 is 77. So this is the processing time, and at what minute what job is on what machine is clearly seen here. The total elapsed time means the first job going on to first machine to the last job coming out of the last machine is the total elapsed time, which is 0 to 77, which is 77 minutes. Now let us also calculate the idle times. Idle times are calculated for the machines unless otherwise specified. So let us calculate the idle time for turning machine first. So first job has gone on to turning machine at the 0th minute itself. From 0 to 2 it was with 4th job, from 2 to 7 it was on 3rd job, from 7 to 10 it was on 1st job, from 10 to 21 it was on 6th job, from 21 to 23 it was on 2nd job, and 33 to 42 it is on the 5th job. So from 0 to 42 minutes it is completely busy. But where did it wait? Unless all the jobs are completed in all the machines, the new cycle is not allowed to begin, right? So the last job is going out of the last machine only in 77 minutes. So the idle time for turning machine will be our 77, the total time, minus this 42, because till 42 minutes it was busy. Sorry, this 42, it was busy till this, but after that up to 77 it is idle, which is nothing but 35 minutes. Now let us check for threading machine. So for it to start working on, it waited for up to 2 minutes because it has started its cycle from 2 minutes. So 0 to 2, 4th job was on turning machine. Only after this 2 minutes is lapsed did it come to the threading machine. So it waited for that 2 minutes plus. So threading machine waited for this first 2 minutes. Then from 2 to 8 it was busy. Immediately in the 8th minute 3rd job has come and it worked on it for 12 minutes. From 12 to 20 it was again busy on job 1. And after this job 1 is completed at 20th minute, it had to wait for 1 minute for job 6 to come. So there is a difference from 20 to 21, which is 1. Now from 21 to 22nd minute it worked on job 6, and for job 2 to come, job 2 did not again start from 22nd minute, it started at 33rd minute. So that difference is there, which is 33 minus 22, which is 11. And from 33rd minute it was busy on job 2 for 39 minutes, and from 39 it had to wait up to 42nd minute. So 42 minus 39 is a waiting time for threading machine, and from 42nd minute it was busy on 45th up on job 5 up to 45 minutes. Plus, for the new cycle to again begin, it should wait until all this is completed. So this 77 minus this 45, it was busy only till 45 minutes, so it should wait for this long. This comes out to be 49 minutes per cycle. Now some of you might have a question that even after this much of time, means even after it waited for 77 minus 45, why are we not again adding this 2? This 2 is again an idle time for threading machine. We will add that idle time only for one cycle, which we added here. So I will add this for the next cycle again. I will not add that 2 again here. So in that fashion, for threading machine, the idle time came out to be 49 minutes. Now let us see with the knurling machine. For the first job, which is job number 4, it had to wait for up to 8 minutes. Only from the 8th minute that job 4 came onto knurling machine. So it waited for that 8 minutes. Plus, let us see. From 8 to 20 it was busy, from 20 to 29 it was busy, from 29 to 42 it was busy, from 42 to 55 it's busy, from 55 to 69 it's busy, from 69 to 77 it is busy. So it's clearly the idle time for knurling machine is only 8 minutes. In a similar fashion, if at all you need, you can find the idle time for a job also. Like for example, job 4 did not wait during the machining time, but job 4 completed its work on all the 3 machines within the first 20 minutes. So idle time for job 4 will be the total time 77 minus 20, which is 57 minutes for job 4. So unless otherwise specified, the idle time is calculated for the machines, but even if you want to find the idle time of a job also, you can do it from the table.
Thanks for watching. If this video was of help to you, please like it and share it with your friends. And don't forget to subscribe to our channel.